Okay, so you're asking why our products are never here, or reactants are never here. Okay, that is because we start with this, right? Then we let it turn into N2O4. Okay, so when we did the zinc plus HCl, okay, we started with our two reactants. Okay, they had a concentration, right? Then we put them together and their concentration decreased while our products increased because we started to create it now. Okay, so at the start, when we start, we have a lot of our reactants. Okay, then our reactants react and make our product. So our reactants are turned into our products. So our reactants concentration will decrease while our products will increase at the start of a reaction. Okay, so now let's look at the second graph here. Once again, we have a decrease in temperature, right? So if we decrease our temperature, our exothermic reaction will be favored. Okay, so which reaction will be favored here, the forward or the reverse reaction? The forward reaction. If we decrease our temperature, yeah, we decrease our temperature. Yes. Okay, now exothermic is our forward reaction because they tell us that. Okay, so we have our reaction that happened here. We reached a equilibrium. Then we decreased the temperature. So now our reactant's concentration decreases further because our forward reaction is favored. So we take our reactants and turn them into more products. Okay, and if we look at from the product's point of view, we had our initial reaction. It reached an equilibrium. We decreased the temperature, so our forward reaction is favored because it's our exothermic reaction. Okay, so we will take the nitrogen NO2 and turn it into more N2O4. Okay, forward reaction is favored. So our products concentration will increase. Okay, not too bad yet. You still, guys, all still with me? Okay. Now we have our reaction rate versus time graph. So a change in temperature will affect both of our forward and reverse rates. Okay, remember we said here the rate of both of our reactions will increase. So if we look here and we see once again we have our solid line which is our forward reaction. Okay, so this is not, oh wait, I'm not going to use pink, let me use green. So our forward reaction, okay, and our dotted line is our backwards reaction. Okay, so if we increase our temperature, will the forward or backward reaction be favored? The backwards ones, because it's our endothermic reaction. So our brown reaction will be favored. And you can see this, right? Because we have our reaction rate, then we reach our equilibrium. Then our backward reaction is favored. So it jumps up the most, okay? And then a new equilibrium is established. Okay, if we look at what happens to our forward reaction, we have a small increase in the rate, a quick increase, and then it continuously increases again. So then we have our decrease in temperature. Okay, yes, our exothermic will be favored. Okay, because we take heat away, we want to put more heat in by favoring our exothermic reaction. And our exothermic reaction is our forward reaction, so it is our green reaction. Everyone that's taking part in the minute to win it contest today must come together at the back of the personnel room. Yes. So you guys know where the door to the kitchen is? Yes, I think there, because they said at the back of the personeelkamer. Okay. So if we have a decrease in temperature, our exothermic reaction is favored, and in this case it will be our forward reaction. So we look at our forward reaction, the green one. We reach our equilibrium, and then it falls down only a little bit, right? Okay? The backwards reaction falls down a lot. Okay, so that is because the forward reaction is favored. So the reaction rate decreases only a little, okay, before we reach our new equilibrium. Okay, so that is our effect in temperature. It's not that bad, okay? So we add our concentration. We decrease and increase the concentration of our products and our reactants. We saw what happened to it. And we looked at our graphs and what happens over there. So now we are going to go through 2 examples here. Okay, I forgot this page existed. I thought we were going to the problem now. Okay, so we have our exothermic reaction with delta H smaller than 0. So if the reaction is heated, okay, if we add more heat, if we add temperature, okay, the yield of the products will decrease to compensate for the effect of heating. Okay, so now they explain it not in terms of our exo and endo, okay, because we know now our forward reaction is exothermic. That means our reverse or our backwards reaction is endothermic. Ooh. Okay, so now they tell us if we increase the temperature, if we heat it up, okay, our yield of our products will decrease, okay, because our endothermic reaction will be favored. So our reverse reaction will be favored. So our products will be taken and turned into reactants once more. So our yield of products will decrease. Yield, okay, do you not remember percentage yield, right? Okay. Okay, so yield, oh goodness, how do I explain what yield is? So if we do a chemical reaction to make a specific product, so we can sell that product, right? Okay, as you all know, life isn't perfect, so a lot of stuff can go wrong. Not all of your reactants will react together. So theoretically, right, we know that at least this much of our product must form, right? We did those calculations. Okay, but then actually only so much of the product will form. So the product that forms is your yield. That's what you get from the reaction. That's what you can use to sell. Okay. So when our reaction is heated, okay, the products will decrease and our Kc value will decrease. Our equilibrium constant will decrease. Okay, now very important to remember, this is specifically for exothermic reactions. Okay, you'll see on the second half of the page we're going to do the same for an endothermic reaction. Okay, so if our reaction is cooled, we take temperature away, right? Which of our reactions, forward or backwards, will be favored? Forward. Okay, because it's our exothermic reaction. So we take heat away. La Chatelier says we want to put heat back. Okay, so exothermic reaction is favored. So the yield of our products will increase, right? Because our forward reaction takes our reactant, turns it into products. Okay. And our equilibrium constant will be increased. Okay, so now they tell us the Kc value or equilibrium constant for a reaction is always given at a specific temperature. So for example, in this example you can see they tell us a temperature and they tell us the yield. Okay, in this one they show us, let me see if they actually do. No, they don't, because we are going to change the temperature. Anyway, so they will always say this reaction happens in a flask of this size at this temperature. Okay, so they will always give the Kc value at a specific temperature. Right? Because also we know now when we change the temperature, our Kc value will change. Okay? So it makes sense that if they give you a Kc value, you are going to have to, what do you call it? Okay, so if they give you a Kc temperature, that Kc value must have been measured at a specific temperature. Okay, that's what I wanted to say. Now we have this reaction, the same one we've had now for a while. Oh no, it's a different one. Okay, we have nitrogen gas reacting with hydrogen gas to form ammonia. Okay, and they tell us delta H is equal to negative 46. So this is a exothermic reaction. So now they ask us explain why the yield at 635 Kelvin is 3 mole and at 1000 Kelvin it is 0.5 mole. Okay, so the yield, how much products form. Okay, so we have 3 mole at the lower temperature and 0.5 mole at the higher temperature. So now I'm going to go through this with you guys and see how to explain this. Okay, so this reaction, by the way, is a Haber process. It is one of the industrial processes that we are going to do in this chapter, because as you all know, ammonia is used a lot in cleaning products. Okay, so it's something that people want to buy so that they can make their cleaning products. Okay, so our forward reaction is exothermic. Okay, we are explaining why the yield at a lower temperature is 3 mole and at a higher temperature is 0.5 mole. Okay, so we're explaining why at different temperatures we get different yields. Okay, we get a different amount of products that form. Okay, so our forward reaction is exothermic. Okay, and if we go from the 635 to the 1000 K, okay, our temperature is increased. The temperature was increased. Okay, now we're going to do something very frustrating. Okay, we are going to say according to who? Nice, Le Chatelier. So according to Le Chatelier's principle. Okay, what does Le Chatelier's principle say? It says the reaction that, okay, now the reaction, sorry, let me just look at it in English. Okay, the reaction that opposes, okay, the reaction that opposes okay, so our reaction that opposes the disturbance will be favored. Okay, wait. Yeah. Okay, so thus the endothermic reaction will be favored. Okay, right, because we added heat. The system wants to take that heat away. It does that by favoring the endothermic reaction. Okay, so the endothermic reaction will be favored. This is the reverse reaction or the backwards reaction. Okay. This means the concentration of our products will decrease. Thank you. I'm so glad. It sounds like you guys understand this. So the concentration of our products will decrease and the Kc value, yes. Okay, so why will the Kc value decrease? Okay, there's too much of you talking. Put your hands up if you want to try and answer. Okay, so why will our Kc value decrease? Okay, now come on, you were talking. I can't hear if three of you talk.
I'm just listening right now. Okay, so because the yield of the products constant for the effect of the heat.
Okay, so our Kc value is equal to what? The concentration of our products over the concentration of our reactants, right? Okay, so our Kc value is directly proportional to the concentration of our products. So if the concentration of our products decrease, the Kc value will decrease. Okay, so yeah, at the bottom, I'm just going to write, because our Kc value is directly proportional to the concentration of our products. Okay, are you guys finished writing or should I leave it here for a while? Okay. Okay, you guys done? Okay, so let's just quickly, I'll put it on the screen again now. Let's just quickly go through the endothermic reaction as well. Okay, so endothermic means delta H is bigger than 0. So if our reaction is heated, we add temperature, we add heat. Okay. The yield in products will increase, okay, and that means our equilibrium constant will also increase. Okay, so we have an endothermic reaction, which means our forward reaction is endo, and the reverse reaction is exo. Okay, so if the reaction is heated, we add energy. Okay, we add heat. The system, according to Le Chatelier's principle, will want to remove heat, right? Okay, so our forward reaction will be favored. So our forward takes our reactants and turns it into products. Okay, so our products will increase. Okay, last one, if the reaction is cooled, if we take away heat, if we take away temperature, the yield of our products will decrease. Okay, we take temperature away, so the reaction wants to put temperature back. How does it do that? By favoring our exothermic reaction, which is our reverse reaction. So it takes the products and turns them back into reactants. Okay, and our Kc value will decrease. Okay, so I want you guys, so we have another example here. We start with N2O4 and we turn it into NO2. Oh, isn't that just NOS? Okay, anyway, NO2. It's that button they push in Fast and the Furious to make the cars go faster. I think it's NO2. Nitrous oxide. I think. Anyway. Okay, so we take N2O4 and we turn it into NO2. And we have an endothermic reaction. Now they ask us, how will the concentration of the products be influenced when the temperature is decreased? Okay, so now I want you guys to use this same recipe. Tell us what the forward reaction is. Tell us what we did to the reaction mixture. What happens according to Le Chatelier's principle. And what that means for the concentration of the products. Okay, I'm going to give you a second to do that. Did I write exothermic? I did. Ah, you went wrong. It was me all along. It's endothermic. But the rest I think will be right. Yeah. The last year's... Oh, no, never mind. Okay. So our forward reaction is endothermic. And our temperature was decreased. So according to Le Chatelier's principle, the reaction that opposes the disturbance will be favored. Thus, the exothermic reaction will be favored, which is the reverse or backwards reaction. So the concentration of our products will decrease and the Kc value will also decrease. Okay? Yes, that's all I want to say. Okay, so this is our change in temperature. Okay, so now, are you guys finished writing? Okay, so we'll look at question number 20. So it was June 2022's exam, so 2 years ago, about how they ask about these questions. Okay, so this isn't in your notes, so it's in the old exam papers. Okay, so I wanted to give you guys a break about for all this forward and reverse because we still have 2 factors left to do and give you an example about how this will be asked. Okay, so initially 4 moles of hydrogen gas and 4 moles of iodine are allowed to react in a sealed 2 cubic decimeter flask according to the following balanced equation. Okay, what do we see here? Exothermic. So the graph below shows the concentrations of our hydrogen gas, one of our reactants, and hydrogen iodine, which is our product, versus time during the reaction. So we have our reactant, and we have our product. Okay. Okay, so this is our concentration versus time graph. Okay, so if you get a graph for this, go look at which one it is, if it's the rate of reaction or if it is our concentration. Now they ask, write down the value of Y. Oh, Y, here. Okay. So, it is 4 moles, but this is concentration. Okay, so how do we do that? How do we go from moles to concentration? Concentration is equal to volume over... No. What? Concentration is mole per... Oh, sorry. Concentration is mole per volume. N over V. N over V. Okay? We know our moles, they give it to us as 4. And the volume they also give us, as we can see, hydrogen gas, it's a gas. Okay, so it's going to fill this volume up completely. So volume is 2 cubic decimeters. So we have a concentration of 2 moles per cubic decimeter. Okay, so this is Y's value. Yes, we are given them all. Okay, but we can't use the mass because this is a gas. Okay, we can't weigh a gas. Okay, so state Le Chatelier's principle. Okay, so definition that you will learn for the exams: when the equilibrium in a closed system, okay, when in a closed system is disturbed, the system will reinstate a new equilibrium by favoring the reaction that opposes the disturbance. Okay, Le Chatelier's principle, definition, learn it. Okay, then they ask changes were made to the temperature of the flask at time T2. Okay, so we reached an equilibrium here. You can see that, right? We made a change and a new equilibrium was established. Okay, was the flask heated or was it cooled? Okay, so let's look at this, right? It's a exothermic reaction. Okay, it's always keep it in the back of your mind. We are exothermic reaction. So we can see that our product's yield increases. So now if we look here, where the yield of our products increase, that means the reaction was cooled. Okay. So you understand? Okay, so the flask was cooled. Okay, it was cooled down. Fully explain the answer to your question. Then you do this whole thing once again. Okay? Our forward reaction is exothermic, our temperature was decreased. Okay, now because we already stated Le Chatelier's principle, you can just say, according to Le Chatelier's principle, okay, the exothermic reaction would be favored, and this is the forward reaction. Okay, so we did it for the other one. Okay, this means the concentration of our products will increase and the Kc value will also increase. Okay, so for this question, 2.1.4, you go write down this. But because they already asked you to define Le Chatelier's principle, you don't have to define it in your answer again. You can just say according to Le Chatelier's principle. Okay, and you see this counts 3 marks and 2 marks with the Le Chatelier's principle. So this whole thing can count anything from 5 to 6 marks. Okay. Okay, I'll wait. Okay, because the bell is going to ring very soon. When is the bell going to ring? I don't want to go on to the next part of this question. When does the bell ring? This is 4th period. Oh no, we still have 15 minutes. No, we have 4 minutes left. Okay, so I'm not going to start the next part because the next part is where we get into our equations and stuff. And I'm not going to do that now. Oh, okay, you want that one? Yes, you can do that now. Okay, so I just want to say one quick more thing. I'll go back to it now. So these two, let me get a nice pink color here. This dot and this dot. And these 2 dots, okay? If you learn them, if you papegaai leer them, okay? If you learn them out of your head, okay? You can always get this right. Because for an exothermic reaction, if it's heated, the yield of our products will decrease. Okay, so those are the 4 different types of situations you are going to get when we change the temperature. Okay, so tomorrow we will finish this question and start with the effect of changing the pressure.